Alright, time for another DraftPhysics.com video presentation. Hopefully not too long a video, but it's just so bizarre. So the Dispar lab guy has done, I don't know, a couple of test videos, sort of, with his a lever, comparing, okay, putting force in one side and force on the other side. So I guess I'll draw it. Now he's done it completely backwards from the what you would call the classic test for kinetic energy, which is surprising, because I guess everyone, including me, thought the results would be uninteresting, but he's actually broken the laws of physics from plainly, which is a big surprise. So anyway, we'll take a look at it. I'll draw that. Alright, so the experiment he is apparently doing, okay, again, is pretty much a backward diagram of the classically described experiment where you put a heavy mass in, okay, a 2 mass, let's say, at one location, and then at 2 distances on the other side you put a 1 mass, okay, half the mass. And the expectation is that the lever, an ideal lever, is going to, move this much here. In the same amount of time, it's going to move this much over here. And therefore, this is going to leave with twice the velocity, and you'll conserve the momentum. So this will have 1 velocity, and this will have 2. Now, he's reversed it. So he's got the 2 mass. Well, I should draw it, I guess, his way. I mean, what the hell? He's reversed their positions also. Alright, so he's got the 2 mass over here on this side, on the lever, presumably. And then he's putting the 1 mass in over here at twice the distance. And so the ideal lever, that's if the lever doesn't do anything to screw it up, the idea would be is that you have a velocity here and that you have to have half the velocity here. You don't really have a choice about it. Whatever motion you have over here is going to be half the motion you're going to have over here. So the expectation is if this has a velocity going in, okay, this is going to have to be half the velocity. There's not really much choice in the matter because of the distance. And he's getting numbers, okay, where, say, this is going, well, we just go in absolute seconds, okay, yeah, his numbers. So he's got around 250, okay, as the speed going in, and he's got 400 coming out. Now, if he was going to get, I think it's 250. Should be able to read it right there, yeah, 250. So, if you were going to double, okay, the way it's supposed to be, then this should be twice as much time, and this should be 500, and there shouldn't be any way to evade that. That would be with an ideal lever. An ideal lever gives you 500. Now he's improved on that. He's got it going much faster, so he's got more. Again, we have free momentum, so it's another free momentum experiment. All right, so he's again proven the idea that you can make free MV in this universe, in this reality. It's possible to put a certain MV in to a machine or a device, and you can get more MV out. Okay, more momentum. And obviously, I don't think so, and especially not in this experiment, because frankly, the rule is, how did you make this lever for what he's proposing to be true? This lever had to go faster than the object. Somehow the lever had to move faster than the object's moving, with a 2 mass sitting on the lever. So with a 2 mass sitting on it, it has to move faster, okay, than the object is moving for you to get this result. This 400 is impossible, frankly, okay, with this going in. And that's with an ideal lever. So obviously it should be going something, it should be going actually more than 500. It should be going something like 550 would be the expectation, because you would lose a little bit to the function of the friction of the fulcrum and a little bit to the weight of the, even though I was using a very light carbon fiber rod, a little thin rod, you'd have the expectation you're going to lose something. So you'd be somewhere around, a guess might be 550. And he's at 400. I mean, way faster. So this is going much faster than twice the velocity. I mean, half the velocity. No, half the velocity would be 500. He's at 400. He's going faster. So come on. Yeah, do we think there's a problem with this experiment? I think there must be. Now, you can't really see much, blah, blah, blah. I would argue that maybe he has the carts way too close, the timing gates way too close to the lever. That kind of motion is screwing it up. Maybe when the cart's coming in, it's hitting the lever and it's twisting and turning. If the cart turns, that turns the card. That means the card is going to look shorter than it really is, so the card's velocity is going to read higher. Lots of things to say, oh, there's an opportunity for a mistake. But I mean, just, at least he didn't title it proof of anything, but he just posts this as if this is supposed to make sense to somebody. First, why is he doing the experiment backwards? I mean, the one you want to see is the real classic one, okay, where you put the two mass in and you get twice the velocity on the other side, you know, presumably creating a bunch of free momentum. I mean, free kinetic energy. You want to see the free kinetic energy experiment fail. You want to see the 1.4 thing happen, not the 1.7 thing happen. I mean, you got the 1.5 answer, which is still wrong. But I mean, just how can you make sense out of this defeating of the whole principle of the mechanical advantage, in the sense that, again, the lever has to actually be moving faster than the object pushing it for these results to be real. They can't be real any other way. Then the lever has to move faster than the object hitting it. And no, come on, you got to know there's a mistake. So we'll play a couple of rounds of this, but I mean, it's simple enough. But obviously, like I said, these timing gates are right on top of the lever. He's trying to get the velocities right at the moment it hits the lever and right at the moment it leaves the lever, and he's probably cutting those moments too short. And somewhere in that is probably the failure of this experiment. He's not using a very good fulcrum, frankly. He's just holding a nail or something that has the, that is the fulcrum. I don't think that could be the source of this error, but it's certainly not a great fulcrum. But anyway, the objects are light enough and small enough that it probably doesn't matter, but it's just not a good way to start. The fulcrum should be as hard, like an anvil. It should be as dense and unmovable as possible. But anyway, it shouldn't have any vibration in it. Let's play some of this. I mean, it has this terrible watermark on top of it, but whatever. So, little fast car goes in, heavy car pops out. Now, I'd say from just observing, you know, again, it doesn't look quite right. I mean, it doesn't look like the heavy car's going whatever. Not half the velocity, but something much faster than half. But who knows? At least he's got a consistent source of energy in, so that's good. Now, the test we still haven't seen, which I'd like to see, is the two timing gates put next to each other and just push a car through them and see what kind of numbers you get. Be nice to just see that. Now, he did do the same mass from the same distance, and he got perfect numbers. So basically almost perfect. The car leaving was a little bit slower. So no, that experiment worked. You know, I'd argue that something went way wrong with this one, though. Way wrong. And why he did this one, again, the question is why aren't we seeing the heavy mass going in and the light mass coming out? Why isn't that the experiment we're seeing? The other part that seems a little suspicious is it looks like the lighter car is going straight through, which means it still has energy. Doesn't look like it's stopping, but you can't really tell from this video. And that would mean it still had energy left over. And so it didn't even use all of its energy, and it gave the other car more than half the velocity. So this is just defeating the whole idea that there's a limitation. So, you know, the classic experiment where you take a 5 mass object and you add 5 to its weight, and then you have a 10 mass object. That one can't do this. That one can't defeat this requirement for the 10 mass to go half the velocity. Nobody's done that experiment and gotten more than 10 mass going 1/2 the velocity, and somehow he's defeated that limitation, and he's now conserving the kinetic energy, or at least some portion of it, where in the 10-ton train, 5-ton train scenario, you can't conserve the kinetic energy. No one can do the experiment and conserve it. So the numbers come out pretty consistent: 260, 255, 264, okay, and in the 400 range. So, and again, it should be 1/2 the velocity. So it's going much faster than 1/2 the velocity. Much faster. Yeah, mouse, come on, play the video. Now he does have the timing gates arranged where he's putting cars through them through one side, which probably makes sense because you want to have it on the sensor side, not the light side. But we don't even know what side of the sensor he's going by, whether he is actually going by the sensor side or the light side. So we don't even know whether he's got that right. So again, it looked like the car went straight through, didn't stop, didn't slow down all the way. So it's only using a portion of its energy and somehow getting more momentum out of the other side. A substantial amount of more momentum. Again, the number should be 500 here, 512, and it's 409. So it's 25% more momentum. Free momentum. And then you could argue, why not just put another lever here and do the same thing and just keep making more and more momentum with the free momentum machine. Alright, so this is 1 mass, 2 distance. So I don't know what that means. Okay. No, I don't. Let's see what that is. 1 mass, 2 distance. No, it's 1 mass, the same distance. He's got his finger right in the middle. So this is the one where it should be equal. What goes in should come out, and that's basically what you get. So this is the thing coming out's a little bit slower. You lose 3%, something very small amount to the lever. So that is just pretty much a great outcome in terms of demonstrating conservation. And then the other experiment, no demonstration of conservation at all. Nothing like the ideal lever. So this is exactly like an ideal lever. His other experiment, completely unlike the ideal lever. Don't know if I can see anything fundamentally different. In the setup, I mean, yeah, I don't. Was this wire in the middle before? Guess I'll have to look and see. Now let me go back and see if that wire was there. Yeah, it was there still. So he didn't change that any. Can't, so yeah, whatever. I mean, frankly, I don't know how somebody can make sense out of it. He made the lever move faster than the car pushing it. It's the only way the other object can be going faster is it has to be that the lever moved faster than the car that hit the lever. The car hitting the lever is moving somehow slower than the lever it's moving, which just doesn't make any sense at all. Alright, so I'll leave it at that. So just more junk, more noise. Said it before, that's all these people are interested in doing, is creating noise, create nonsense that has to be debunked. Go, here's the mystery shit experiment, find out what's fucking wrong with it. It's just such a pile of crap. Alright, I really think it's enough. Yeah, just saying, I don't see how you can possibly make sense out of the experiment. How it's possible for him to get results that an ideal lever can't produce. Realistically, how can you do that? Somebody explain it. How does he make the lever go faster than the thing pushing the lever?